So one of the most probably direct and beautiful representations of how the method of solving differential equation with linear coefficient works is the problem of one-dimensional Coulomb potential. So and let's see how the corresponding Schrödinger equation looks like, and we'll analyze it and build the solution and the quantization of energy level using entirely just the method of the solving of differential equation with linear coefficients. So let's draw our potential function. The problem actually makes sense only for positive values of x. So, and actually it can be well defined only if we impose additional boundary condition, namely if the regions of negative x is impenetrable for the particle. So here we add an infinite wall, and in quantum mechanics that means that the wave function, due to its continuity condition, should vanish at this boundary at point x equals 0. Right, and let's analyze the solution of the corresponding Schrödinger equation. Well, we expect that the particle will have a discrete spectrum, so the energy levels are going to be quantized. So let's see how this comes about from the structure of our differential equation. Here we go. This is the Schrödinger equation. And keeping in mind that we expect our energy to be negative, we are having a bounded wave function. We put it in the form minus modulus of E. In all the calculation, we put the Planck's constant with the bar equals to 0. And let's multiply this equation by 2m, get rid of unnecessary minus sign, and what we get is the following thing: psi prime prime plus x 2m alpha psi equals kappa squared x psi, where kappa squared is 2m, the modulus of energy, and let's denote this factor as gamma. So finally, we arrive at our formal differential equation: x psi prime prime plus gamma minus kappa squared psi equals 0. And kappa squared x psi. And let's analyze this equation using our Laplace type technique. So P and Q polynomials. P polynomial is simply gamma, and Q polynomial is t squared minus kappa squared. Let's perform the integration. And the integration gives us just the log function. Finally, we can write down all our building blocks for the solution of this equation. So first of all, v function, which defines the position of the contour in a complex plane. V function is simply e to xt times e to this integral, right? So it's simply t minus kappa divided by t plus kappa to the power of gamma over 2 kappa. This is a multivalued function, and let's denote it as g of t. Right. And finally, z function, which is this piece of our v function divided by the q polynomial. So, and it gives us t minus kappa in the corresponding power divided by t plus kappa. And the solution, the wave function, looks as follows. And now let's analyze the structure of the solution and build their corresponding spectrum.